Hello everyone, my name is Pablo Samuel Castro from Google Brain, and I'm happy to present our paper MICo Improved Representations via Sampling-Based State Similarity for Markov Decision Processes. And this is joint work with Kastner and Prakash Panangaden from McGill University, as well as Mark Rowland from DeepMind. In reinforcement learning, we're typically starting from a set of unstructured states, and we often want to map them into some function of interest. This could be our state function or our state value functions. But what we typically want to do with deep reinforcement learning is we want to structure these states in some manner that this mapping into the function of interest is of use. What I mean by this exactly is if we take two states in our unstructured states, x and y, and then when we look at them in their structured representation, we would like to know if the neighborhood in that structured representation tells us something about their neighborhood in the function of interest. More formally, what we mean is we'd like to have a distance d that tells us something about the difference in values of these 2 points of interest. You could think of this as an upper bound inequality. If the distance between two states upper bounds their difference in value, then that tells us some theoretical guarantees for these functions of interest. What makes a good distance d that captures these types of properties? In our work, we argue that behavioral similarity is the type of property that we'd like to capture. And so what is a good candidate for this? Perhaps by simulation metrics. Now, what are bisimulation metrics? The way they are computed is if you start with an initial estimate, d0, that assigns some distance between any state, let's say always the distance 0, we're going to apply an update operator, tk, which is going to perform the following operation. It's going to take the difference in rewards and add it to the Wasserstein distance between their next state transition dynamics, discounted by a factor gamma. And we're going to take the maximum action that maximizes this sum. Now this will give us a new metric estimate d1, and we can apply exactly the same procedure to d1 and obtain a new estimate d2 and continue in this iterative fashion. You can see that this is quite evocative of the Bellman update when we're doing this for reinforcement learning. And eventually we are guaranteed to reach a fixed point, which we denote d tilde. And this fixed point is obviously the output when we input it to the update operator. What's nice about this d tilde is that it does provide this type of upper bound that I was mentioning. It tells us that any distance between two states under the bisimulation metric upper bounds their distance in optimal values. And this is quite nice. However, it doesn't tell us anything about the other policies that we may be interested in. In particular, in reinforcement learning, we don't start from the optimal value. We go through a series of iterates until we reach something resembling the optimal policy. So in a paper last year, I presented the pi bisimulation metric, which is similar to the original bisimulation metric, but now it's defined with respect to a specific policy pi. The nice thing about this is that it does tell us something about other pi's. We still have this upper bound, where the pi bisimulation distance is an upper bound on the values for that particular pi. However, this still suffers from a problem in that it still uses this Kantorovich-Wasserstein metric between the next state transition dynamics, which is very expensive to compute. So in this paper, we're introducing a new update operator, which we call tpim, and it's very similar to the pi bisimulation metric, but now we're replacing that expensive Wasserstein, which is an optimal coupling between the next state transition dynamics, with an independent coupling of the next state transition dynamics. And we call this update operator tpi of m. And this will give us the MICo distance. We can prove that this update operator, much like the bisimulation operator, will converge to a fixed point, which we call u pi. And now the question is, what is this u pi? Is it a metric? Is it a pseudometric? Well, it turns out that it's not a regular metric as we would expect. It's something that we've coined a diffuse metric. And there's more details about the interesting theoretical properties of this type of metric in the paper. But I'll just define it here. A diffuse metric is similar to a metric. It obeys some of the same properties, so in particular it obeys symmetry, it obeys the triangle inequality, but the first of the standard properties of a metric, where you have that if two states have a distance of 0, they are necessarily the same state. In a pseudometric you would have that two different states can have a distance 0, but you certainly don't have that a state can have a positive distance to itself. So this is what diffuse metrics allows. We can have a state have a non-zero distance to itself. This may seem a little strange, but it's actually measuring the spread of the transition dynamics starting from the state. So if you have only deterministic transitions, then you would have a proper metric because you wouldn't have a non-zero self-distance. Okay, so again, please check the paper to see the interesting theoretical properties of diffuse metrics, but I'm going to go into how we learn and approximate these diffuse distances. So let's say we start with a state X, that could be an Atari frame, and we feed it through a set of convolutional layers, and we're going to call the output of these convolutional layers phi of X. And then this phi of X gets fed in through another set of dense layers, and we're going to call this psi of X. And then we concatenate these two operators and we get psi of phi of X, and this will be our approximant of the Q values for this particular state X. And this is what we typically do in DQN, and we're going to call this the temporal difference loss. So we can take another state Y with same Atari frames, and it's using exactly the same architecture and the same parameters as we did for X. But now what we're going to do is we're going to take the two representations, phi of X and phi of Y, and we've chosen to make these the representations, and we're going to try to approximate the MICo distance between these representations. And we're going to do this with this parametrized distance u of omega. And this will give us what we call the MICo loss, which I'll define now. So how do we learn this MICo distance? We're going to try to approximate u of pi with this parametrized u of omega of the representations of x and y. So it's important to note that we're not operating on the ground states, but on the representation space, which is given to us by our convolutional layers. And the way we've decided to parametrize this distance is by these two terms here. The first term enables us to have non-zero self-distances. By taking the average of the norms, we are allowing this parameterization to be expressive enough to represent these diffuse metrics that allow for non-zero self-distances. And this second term is what you might expect when computing distances between representations. We're taking the angular distance between the two representations, and we're weighing it by a term beta, which allows us, it's a hyperparameter that we use to obtain better results. Okay, so now how do we train this thing? Well, we reuse the standard replay buffer that we would use for DQN. And so we'll sample two transitions. I'm omitting the action because I'm assuming the policy is fixed. So each one of these transitions will consist of a state, a reward, and the next state. And what we'll do is for every pair of transitions that are sampled, we're going to take the absolute value of the difference of rewards, and we're going to add it to a discounted distance according to our parametrized distance. So now here we're using target networks, much like DQN introduced. And we're going to call this the target of our learning objective. So this term on the right-hand side, this is analogous to the definition of the MICo metric, where we take the independent coupling, and the target is analogous to the update operator that we defined previously. So now we can take the square difference of these two, and this becomes our loss. And the expectation is over the transitions that we sample from our replay buffer. And this is what we coined the MICo loss. One thing worth noting is that the Huber loss is quite important to use here. We were able to get much better empirical results than if we were to use just mean squared error. So how well do these learned metrics do in practice? Well, it turns out they do really well. So we applied this MICo loss to all of the agents in the dopamine library. These are all value-based agents. And we saw that across all the 60 Atari games, when we plot the human normalized scores, we see improvements across all of the agents. In particular, Rainbow, the improvements were quite dramatic. As the agents get better, such as with IQN and Munchausen IQN, the gains are a little smaller, but that is to be expected. What's interesting is that we also tried it on Soft Actor Critic, which was recently introduced to dopamine. We compared against Soft Actor Critic and got much better improvements, and we also compared against deep by simulation control from Amy Zhang et al. In iClear 2021. And this really demonstrates that the MICo loss is quite modular, and it's quite flexible, that you can apply it basically to any value-based or actor-critic method and get improved representations, measured, of course, according to performance. So there's more details and more experimental results in our paper. You can see it at the link below. I also have a blog post where you can read more, and there's an interactive diagram to learn more about the diffuse metrics. And thank you very much.